Hey, AP Physics. We're going to talk about uniform circular motion today, and I will often abbreviate that UCM, uniform circular motion. Well, what means these words? Uniform is the sense of, you probably know what that, uniform, like one form. This means same, uniform. So what's the same about it? It's the speed. And we don't just mean, I guess you could also say the circular. It doesn't mean something that's like sort of circular, like round-ish. It means that it's actually something that's moving in a circular path. The size of the circle's not changing either at a constant speed. That's what that means. So this is another kind of two-dimensional motion. It's an important example. There are lots of things in our world, universe, that move in circular paths, like planets and their moons and stars and around the centers of their galaxies and stuff like that. So it's common-like, and we want to understand it. So before we get right into the physics of it, I'm going to remind you of a couple of math things that we need to have at the ready. Here's a fact from geometry. If you've got a circle and you have some angle, well, let's call it theta, and the circle has a radius of r, then I think probably in geometry, I'm not 100% sure, but probably you called this the length of this sector. You used an S for that, maybe. If theta is in radians, then there's a very nice relationship between these. The length of that sector is theta times r. If you think about the unit circle, what is a radian? Well, a radian is just like the measurement of this. It's using how much arc there is of the circle if the radius of the circle is 1. So if you're on the unit circle, then S is just theta, right? That's what a radian is. What's the whole distance around the unit circle? What's its circumference? 2 pi. And we call that 2 pi radians. So if you scale up or down the size of the circle and it has a different radius, you just multiply by that radius. And that is the length of that sector. Okay, so there's a fact for you. And then also from, I don't know, pre-calc, I guess. You know that if you have a sine or cosine, I'm going to use sine here, but the same thing is true for cosine, with an equation y is equal to a sine bx. So in other words, if we've messed with the scaling of it some, so this a, that's just the amplitude, that would be how much it goes up and down. And then what about this? This is the so-called period of this. It's how much x-axis it takes for one full pass through the function. What's the period here? The period of this is equal to, do you remember? It's 2 pi, it's not b, it's 2 pi over b. And you could also write that, because of math, algebra, you could multiply the b up here, divide that, so you could also do that, right? Those are both true statements about that. Okay, so there's a couple facts that we're going to use in a few minutes. So consider this. consider an object that is in uniform circular motion going around a circular path. We'll say that it's this way. This is what we usually think of as the positive direction for circular motion. Why do we think of that? It's not clockwise, it's counterclockwise, but from math we usually think of angles starting here at 0 and then moving around this way, like through quadrants 1, 2, 3, 4. So it jives better with our math sense, but just like up and down, positive, negative, we get to make the decisions about that. So typically we think of this as the positive direction, but it doesn't have to be. We get to decide. All right, so let's say that this, just so I can do like my nice analytic geometry here, I'm going to go ahead and throw down some axes. And let's say that this circle has a radius of r. And let's say right now, at this particular spot, this thing's moving around like this, right, nice and steady. Let's say it is at this point right here. We could call that point xy, but in fact, if we wanted to get all triggy about it, that's really the point r cosine theta r sine theta, right? Okay, so let's see. If this is moving around at a constant rate, then let's call the speed v. I'm not putting a vector hat on that because this is just the speed. Is the velocity constant here? Think about that for a second. Yes or no? Answer is no. The magnitude of the velocity, in other words the speed, is constant, but the direction is constantly changing. So if you were looking at the velocity vector, it is different all the time because it's constantly changing the direction. The length of it, its magnitude, is constant, but the direction is changing, and so the velocity is not constant, but the speed is. Okay, and another thing we could say is let's assign here let's say that we would like to be able to describe the rate at which theta is changing. So the angular speed of this, and we're going to use a little curly looking W like that. And that is the Greek letter lowercase omega. That's what we use for angular speed. That's going to come back later in the year also when we do more stuff about rotation. So that's the angular speed omega. So if you think about here, of course, speed would be, in SI units, would be meters per second. What's this measured in? Well, this is radians per second. Right? How many radians does it go through per second? That's what that angular speed is. And since S is equal to theta times R, if we think about the derivative of this, like related rates kind of thing, this S and theta are changing with time. Of course, the radius of the circle is not changing. So if I took the time derivative of this, just like we did in related rates problems, then ds dt would be equal to d theta dt times r. But ds dt, the rate at which this length is changing, that's just the speed, v. And d theta dt, well, that's the rate that the angle is changing at. By definition, that is omega. So v is equal to omega times r. That makes sense. And now, our position vector. I'm going to call this r, the vector r, which is changing with time here. Okay? Oh, and I wanted to, sorry, before I do that, let me just go back over here, and as we're defining things here, I do also want to just say that the period, the amount of time that it takes for this to go all the way around the circle, we're going to just use a capital T for that. Not to be confused with lowercase variable time. This capital T is the fixed amount of time it takes for this object to make one lap around the circle. All right, so then my position vector is equal to r cosine theta. This is the fixed radius r, not to be confused with variable vector position. R cosine theta I plus r sine theta j. Now, that's all fine and good, but that doesn't actually give me the, I don't have t's in here. That's the problem here, right? I know that theta is a variable and it's changing with time, but I'd like to have time in here. So can I do something about that? Well, yes, I can. What I need to recognize is what needs to go in here is some kind of expression like that, where I have a number and then times time. So what is the number that needs to go there? R cosine, and I would like to have some expression, something times t. Well, the number that needs to go here, the b, is 2 pi divided by the period, right? 2 pi divided by the period plus r sine, and then same thing here, 2 pi divided by period. But let's think about for a second, what is this angular speed? Well, it's the rate at which the angle is changing, right? So what would that angular speed, like how do we do regular speed? It's, well, that's how much distance it covers in some unit of time. So one way of looking at that would be, since the speed is constant, well, what's the whole distance around the circle? That'd be the circumference, right? And how long does that take? Well, that by definition, that's the period, right? So the speed v, add to our collection of information over here, the speed v is equal to 2 pi r, because that's the distance all the way around the circle, divided by how long it takes. Speed is equal to distance divided by time. That's the distance around the circle. That's the time for going around one lap. And omega, likewise, what's one lap around the circle in terms of like how much theta that is? Well, that's 2 pi, right? That's 2 pi is all the way around the circle in radians. And how long does it take? Well, that's by definition, that's what the period is. So here, the 2 pi over the period here, that actually is omega. So that's nice. Cool. And we have done plenty of little homework problems in our book, since we know about vector stuff and we know some calculus now. The derivative of position is velocity. And I know how to take the derivative of trig functions. There's a little chain rule here because there's an omega inside here with the t. That's just a constant, the radius of the circle. So the derivative of a cosine function is negative sine omega t. Now out here there already was an r, and then the chain rule is going to pop out an omega, right, times the derivative of what's inside. Omega is just a constant, right? It's 2 pi over t. And then the derivative of sine is cosine. Omega pops out there also. Good. And now there's interesting observation here. Well, maybe it's not that interesting, but if you Pythagorize these components to see how big is this vector, what is the magnitude of it, you would Pythagorize this and this, squaring both things. You'd get r squared omega squared sine squared, r squared omega squared cosine squared. The sine squared and cosine squared, you could factor off the r squared omega squared and then take the square root of that. So anyway, if you Pythagorize that whole thing after a couple of brief little algebra steps, you just get r times omega. But of course we knew that already. So that jives with that. This is where things are a little bit more interesting, I suppose. How about the acceleration? Well, let's see. Take the derivative of a sine function, that's cosine, and another omega is going to pop out because of the chain rule. Plus, same deal here. Oops, so I jumped the gun on that plus because the derivative of cosine is minus sine. Another omega pops out there. Not sure where the edge of that screen is for you. I'm going to scoot over just a little bit. All right. And by the same kind of Pythagorizing argument that we just made here to confirm that the speed is just omega times r, here, what is the magnitude of the acceleration? So I'm going to write a without its vector hat. That means I'm just talking about the magnitude of it. Well, I would Pythagorize these, just like we talked about here. Sine squared plus cosine squared. The minus signs don't matter because we're squaring things. Just interested in how long is the hypotenuse of a triangle with those legs. So cosine and sine, when you get those squared, this is going to factor off those. Sine squared plus cosine squared is 1. So we're just going to get that the magnitude of the acceleration is omega squared times r. And doing a little substitution if you want to, if you happen to know the speed and not the omega, then it's also true that the acceleration is equal to v squared over r, just because of this. I need to make a little substitution there. How about the direction? What is the direction of this acceleration? And before I say anything about that, you might be wondering to yourself, wait a second, if this thing is going at a constant speed, then there is no acceleration. But that is not true. Remember that we're talking about two-dimensional motion here, and there most definitely is an acceleration because the direction of this is changing. The direction of the velocity of something does not change for free. If the direction is changing, there is acceleration that's making that happen, right? The velocity is a combination. It's two pieces of information: how fast and in what direction. If either of those things is changing, or both, then you have acceleration. So here, this is kind of like a magical acceleration here. It's just exactly the right amount of acceleration to change the direction of this thing, but not the magnitude of it. So it goes in a circle have exactly that radius. So you can't, I mean, it has to be just so to cause this kind of circular motion. Oops. So what is the, this is the magical magnitude. If you want something to go at this speed around a circle of this size, this is the magnitude of the acceleration that it must have. And in what direction does it point? Well, take a look here. Look at the direction of our position vector r. Its direction is cosine sine. Now this is just the same number, right? A constant times this cosine sine. And look at this one. It's negative constant times cosine, negative same constant times sine. So this has a direction of cosine theta sine theta, and this has a direction of negative cosine theta, negative sine theta. So if this is pointing in this direction, the acceleration vector is pointing in exactly the opposite direction. So how would you describe that direction? That is toward the center of the circle. And just like the direction of the velocity and the direction of the position vector also, this is constantly changing. So as it moves around the circle, the direction is always toward the center of the circle. How about that? So the acceleration has a magnitude of omega squared r, or v squared over r, and the direction of that acceleration is toward the center of the circle. And we call this here, we're going to subscript that with a little c there. This is centripetal acceleration. If you are a student of Latin, then you may understand centripetal is the meaning of this is center seeking, that this is something that is seeking this, looking for the center, or something like that. I never actually studied Latin, but I do know Dr. Bradley, so there's that. And that's basically what you need to know about uniform circular motion. So the rest of, well, I'll do the problems for you. I'll put up a video with those. With a little bit of practice, these problems are really not very hard. Now, if you're looking at all of this, and this like stresses you out, let me just highlight here the things that you need to know. This is one of those situations where, like, being able to reproduce this proof or this derivation of these relationships, that's not really what we're about. But of course, you need to know where it comes from. I'm not just going to drop some random physics equations on you. Like, it would kind of stink, I think, if I just told you, okay, centripetal acceleration, here it is, and like skipped all this. So what do you need to know? You need to know this. But I'll tell you, eventually when we start having equation sheets, like the College Board Physics equation sheet, there's a lot of stuff. For example, this right here, that is on the College Board equation sheet that you get to have when you take the AP test. This is not. Why isn't this? I think this isn't because they just think this is obvious, right? I mean, if you're moving in a circle, well, that's the distance around the circle, and that's the time it takes. So, I mean, speed is just distance over time. So that's not on the equation sheet. This, I believe this is. This most definitely is. And I think that those are the main things that we need to know. Right? And then just understanding the basic context of a uniform circular motion problem. That's it. So I think from there, you got to try a few problems. Please remember that the best way to do that, if you are in fact interacting with the video, if you're doing these in virtual instruction mode, then try a problem, look at the solution video, try another problem, look at the solution video as needed and bounce back and forth so it feels like you're doing the problems with someone. Okay?